Hello, ladies and gentlemen. Good to see you again. Thanks for tuning in today for what is the 12th lecture, part of GGS 300, Quantitative Methods for Spatial Science. Today I'm going to be focusing on inferential spatial statistics. So just before we get going, I hope if you're watching it after the 22nd of November that you've now completed the second midterm exam, and I hope that you managed to make good use of that time which you had, the extra time, in order to prepare fully for that. So fingers crossed we get some good marks from that particular exercise. And then also please don't forget that the next assignment is due just before Thanksgiving, so on the 25th of November. So I hope that you're all on track to complete those pieces of the course on time. Let me know if you've got any questions. I think one thing that I just want to point out is that we've been fairly fluid with the course structure because, ultimately I've been adapting it so that you guys perform to the best of your abilities. I don't want to set you exams or coursework if I feel like you're not prepared. And particularly with COVID, things have kind of been a bit up in the air as to how you engage with the course. So I've been fairly flexible on what we've been doing. I thought, therefore, it was just appropriate for me to basically update the course outline, which I've now done. Pretty much all of it is essentially the same. I just updated the course schedule essentially and just made it a bit clearer as to where we've had particular gaps and essentially what we've got to do in the remaining part of the course, because I know that that's really what you're going to be interested in moving forward from here. So we have the inferential spatial statistics piece this week, as I've already mentioned, and then we essentially have correlation and regression, so two really important topics in order to finish what I hope has been a really exciting and fun term. I've definitely enjoyed working with you guys on this, and I hope that you've enjoyed some of the statistics that we've learned and the case studies that we've been through. Okay, so let's get back to the actual structure for what we're going to do today. Oh, as I've already mentioned, this is the progress. I put it in the slides, but you've got it also in the course update now, so it's there for you if you want to peruse at your leisure. So let's get to the real issues. So, the first part of the course, as I always say, was based on that kind of descriptive statistical approach, and we did within that some descriptive spatial statistics. We then moved on to a whole range of inferential statistics over here, where we might formalize a hypothesis and then essentially go out and try to develop formalized statistical models to understand if this hypothesis is potentially supported by the data. And within that, we've done actually quite a lot of spatial statistical tests. So they haven't necessarily always been explicitly taking into account, things like distance, for example, which is going to be a key part of spatial statistics. And that's therefore why we have this module today, because we're going to be picking up on those kind of spatial statistical tests which explicitly take into account geography. So let's go over some concepts before we begin. As I've already mentioned, on the descriptive spatial statistics side, we were essentially focusing on central tendency for spatial patterns. So central tendency, I hope you now know what that is. So the likelihood that data points are going to cluster around those key statistics, which are focused on the center of the distribution. So the mean, the median, for example, and that's interesting. That can tell us a lot. The other thing that we were asking was, how much dispersion is present within the data, how clustered the data points, how far apart are the data points. But that wasn't necessarily formalized in the way that we then kind of state hypotheses and test them. So obviously we're moving now into that area, as I've said already. And one of the key aspects of this, and actually it's very similar to those other statistical techniques that we've done in the past couple of lectures, is essentially this kind of question of, well, has this spatial pattern just arisen at random, or is there enough evidence for us to state at some confidence level that the spatial pattern is significantly different from points that perhaps have just occurred at random? Okay, so I hope that that's somewhat clear to you, and if it's not, then hopefully you'll grasp it as we go through the lecture. But that's going to be a kind of fairly similar pattern to what we've seen in the previous statistical tests, just with a bit more of a spatial science focus. So spatial patterns, we are spatial scientists. We're interested in things that happen in space, why they kind of happen in the way that they do within space, why they take place, where they are within space. And therefore, we're interested in the patterns of both points and polygons, for example, by the time we actually boil down those kind of spatial statistical patterns into some of those key geometry-based features which we use. So, a point being just two coordinates, an x and a y, indicating where this single point exists within a two-dimensional space potentially. Or polygons, so that's just essentially an object where you have multiple points, a minimum of 5, and essentially if I was to show you what that would look like, the smallest potential example would just be 5 points, and you would just have a square, for example, and you would go around the square, drawing a boundary, and then the final point is actually the same as the first point, and that's how you close the polygon. So, I think you've come across points and polygons before, so I don't need to get too into this here. I assume you've done that within the other GIS modules that are provided by the department. So we're interested in 3 general different patterns, so clustered, so where you have lots of points, for example, or types of areas, types of polygons occurring within one specific space. Dispersed, so basically the antithesis of this, so the opposite. So that's where your points or your cluster, your points or your areas are essentially the opposite of clustered. They are dispersed across space, and then you have just a random distribution. So I could just randomly generate a bunch of numbers between 0 and 10 and allocate them to coordinates, and that would just give me a randomized set of points between those latitude, longitude ranges, which I just stated, so 1 and 10. Anyway, I don't want to get bogged down in that too much here, but those kind of principles come through in how we actually carry out these spatial statistics. So we're interested in working out whether we actually have non-random spatial patterns. Okay, and hopefully these diagrams here, which are on this kind of these two-directional scales, so we have dispersed over here, and then we have very clustered over here, and then in the middle you could have some degree of randomness, for example. So neither dispersed nor clustered. And the question is, well, do we see these patterns actually occurring in society, in the economy, in the environment, in all of those systems that we end up studying, essentially? And the one topical example is how people vote and how people vote in presidential elections. So the question here, obviously, is, well, do how people vote at the county level appear to be, randomly distributed, or are they dispersed, or are they clustered? And I'll let you make a a stab at what you think. But I've got results here for the 2008 election, so Obama versus McCain. And we've got the 2016 presidential election here, results by precinct, so Clinton versus Trump. And I think if you were to actually run some statistical analysis on this, you would find that they would be quite highly clustered. And that's for a range of social and economic processes, which are also clustered in space, which often can influence how people end up voting. So I don't have the new results. It's a bit too early still, but maybe I'll have them for next year. So I've mentioned this before, spatial autocorrelation, and it's something which I brought up when I was issuing the kind of baseline survey to kind of understand where your understanding is at the very start of the course. And I asked whether you had encountered, this idea of spatial autocorrelation. And the reason why I was asking you that is that it's a fairly central concept to how we carry out spatial inferential statistics. Is something that you need to be aware of, and it's something which plagues so many statistical analyses if the analyst doesn't recognize that this is a process which is going on, because it can cause a lot of issues to your results, particularly as we get towards regression. I'll emphasize why, but essentially, this problem of spatial autocorrelation can end up creating junk results. It can inflate your coefficients, and that can have an impact on your p-values, and basically you can draw a whole load of inferences which just don't exist. And one of the reasons why is because we draw artificial spatial boundaries on top of spatially autocorrelated processes, and that can lead to the contravention of that key assumption, which we've used in many of the statistical tests, which is that your sample points are independent. So essentially, they're not independent; they're actually correlated because of this autocorrelation process, and because we're imposing these statistical boundaries onto these processes, which take place over larger areas. And actually, it all kind of comes back to Tobler's first law of geography. So I don't know if you already know Tobler, but this is something which you will probably hear many times if you haven't already. And that's that one of the first laws of geography is that things that are very close together are more likely to be similar, whereas things that are far away from each other are more likely to be different, essentially. So everything is related to everything else, but near things are more related than distant things. So that's in Tobler's words, Tobler's quote. So this is, a central way for us to kind of understand this spatial autocorrelation effect, whether that's elevation, temperature, income, population density, however you look at it. So I was actually just poking around online to look at some good diagrams to kind of help us understand this spatial autocorrelation process. And actually, I came across this person who's written this book, who's actually at a small liberal arts college up in Maine. And I was actually really impressed with some of the content on here. So this person, Gimond, has actually uploaded this kind of spatial analysis book onto GitHub. So if anyone doesn't know, that's just a code repository where you can upload your code and it's open access, and you can actually write books and upload it there as well, with Markdown language. So you can write code which forms as text, basically. So anyway, long story short is that I like some of the diagrams which he had created, and this is a good one for understanding spatial autocorrelation. So essentially, spatial autocorrelation is a measure showing how much a spatially arranged variable is correlated to itself through space. So over here we have the population density map of the US, and we have an elevation map of the US. And as I said before, these are spatially autocorrelated processes. So we are imposing these census, these county boundaries on top of these processes which transcend these areas. So this is an autocorrelated process, and we know that because if these effects were just randomly distributed, they would look like this. Okay, so on the right hand side of the screen here, and you can see there's really quite a significant difference between these two different features, and that's also the case for the elevation map down here. And I think when you look at it in this way, okay, so we have an autocorrelated process over here, and then we have a randomly distributed process here. I think that kind of puts into context the discussion which I kind of pitched to you when we thought about the voting patterns for different presidential elections, because actually here now you can see that these are in reality highly clustered, whichever election you look at. So I think that if these were county, then these must be maybe census tract. Oh, sorry, by precinct. So really quite small geographies, but you can see the difference. Okay, so that's spatial autocorrelation. What does it mean? What's the relevance of this, and how do we kind of interpret it in terms of a measure? And basically, we have a quantitative measure for spatial autocorrelation, and that quantitative measure, that index, can essentially be positive, or it can be negative, or it can be zero, so it's non-existent essentially. And if you have a positive measure of spatial autocorrelation, that basically means that near things are actually quite similar. Whereas if you have a negative spatial autocorrelation, which I haven't seen too many times, at least in my work, then actually that means that near things tend to be really quite dissimilar, so quite different. And then 0, so I have seen this a couple of times, and it's generally that's quite a good sign when you get to 0, because it means that you don't have to move into some of those statistical tests that try to account for the spatial autocorrelation. So I mean, if you've got a 0 and you're intending on running some multiple regressions, which is what we did recently, then actually you would be able to justify just using a standard regression-based approach. Whereas if you had, significantly autocorrelated data, then you basically have to think about potential techniques like geographically weighted regression, which can try to correct for some of those autocorrelation processes and try and control for those types of inflationary effects that can take place on your regression coefficients and then influence your p-values and kind of the way that the statistical model for how you understand the world. Okay, so anyway, not to bombard you too much, we have these 3 different potential outcomes, and let's just think about those visually. So on the left-hand side here, we have positive spatial autocorrelation. So basically where near things tend to be very similar. So that's actually not that dissimilar from the patterns that we saw when we looked at the population density distribution in the US or the voting structures in the US. There could be no spatial autocorrelation. So essentially this would just be a random pattern, as you would see here. So there's not really any discernible pattern from this particular case. Or we could have a negative spatial autocorrelation. So things that are near basically are very different. So this could be the type of outcome that you could get. Variograms. So these are a variant on scatter plots, essentially, and they show how variation in values relate at different distances from a point in space. So it's one way in which we can understand these types of spatial differences by explicitly including distance as one of those key metrics. So I've got 2 examples just here. Essentially, within a variogram, we have a line of best fit, and that's here to basically highlight the main relationship. So you can see that here with the black line, and here as well through all of these scatter plot points. And then there's 3 individual important parts of the variogram which you just need to be aware of. So the nugget, so just down here, so this is the uncertainty when measuring locations close to each other. The range, so this is the distance at which difference in attributes are no longer correlated. So if we look over here, we have an effect here as we're moving away from the measurement point in terms of distance, and the variance is changing. And at some point then we just get a plateau. So we can keep moving away from a point in space, but there'll be no difference in the level of variance. And that's essentially because we've crossed the range. Okay. So this is beyond the point at which that there could be some correlated effect between, space and some metric of interest. And then the CIL as well, so the variance at which the distance and attributes are no longer correlated. So that's this distance here. Sorry, I'm avoiding using the word distance because we already have that on the x-axis. So this measure here, this particular quantity of values. So let's think of that, away from the kind of theoretical part for how to understand the graph in terms of what it actually means. So here, as I already said, on the x-axis we have the distance. So let's just think of this in kilometers, for example. We start at a point in space where we measure, and then we get further away from it. And then we have variance here. So let's just think of this as, if it's 1, then there's less variance, and if it's 4, then there's more variance. So things are very different. And essentially what we're saying here is that if we're close in at short distances, then there's less variation. Whereas if we're up here, then basically larger distances, we've got greater variation. Okay, and then hopefully you'll be able to kind of understand that logic as well in terms of how we look at this second graph, which actually focuses on community dissimilarity. And this time we've got distance in meters. and on the y-axis, so that's the x-axis, we've got distance in meters, and then on the y-axis we've got the level of dissimilarity. So down here at 0.2 things are more similar, and up here at 0.26 things are less similar. So essentially, when we get to greater distances here, maybe over 250 meters, then we have less similarity than if we were down here within the first tens of meters close to the measurement point. Okay, so that's just one particular way for you to think about how these effects play out across space, and then actually visualize it in terms of a two-dimensional plot, a graph that you can place into perhaps a report or something like your dissertation, if you're interested in understanding how these spatial processes kind of play out across space. So why does it matter? Well, we need to understand how distance has an effect on a certain model. So if we are modeling a process and we ignore space, we may not be picking up the main dynamic, which is driving some of that change. And that's because, maybe if people are closer together, there's greater interaction, and that means that there's greater flow of ideas, and that might have an influence on behavior, and that leads to different spatial outcomes. As I already mentioned, spatial autocorrelation does present a serious statistical challenge to the kind of classical frequentist statistical techniques that we've covered in many of the other classes of this lecture. And that's because, it doesn't always include independent random sampling. So we basically break some of the fundamental assumptions included in all of those tests. So you'll remember in the McGrew book, for many of these tests, we have this kind of blowout box here, where it states the assumptions that are required, and if you look at those in these blowout boxes, it will say that independence of samples is essential, and that's basically why this is kind of something which is going to cause you problems if you want to use some of those classical techniques. Okay, so I've already mentioned that understanding space in this way, understanding processes in this way, provide you with insight into the spatial structure of a certain process. But also this can kind of affect how you measure. It matters how you measure it, essentially, and you can do that at the local level or at the global level. So you can do it for a few points in your data set, a kind of sample local measure based geographically somewhere, or you can just do it for all points. So you can just do a global analysis. So let's say you sampled, you had data for Virginia State, and that would just be your global population. You could do a global measure of autocorrelation across the entire study area. Whereas actually you could do local spatial autocorrelation analyses specifically for Richmond or Fairfax or Manassas, and that would provide you with a different level of insight to what you'd be getting at the global level. Neighbor analysis. Okay, so we're moving on now to actually understand a new type of technique and how it's going to affect a new type of an analytical technique which we can use to understand the proximity of different entities. And there's actually multiple ways to determine if two geographical entities are neighbors. So we could create an adjacency matrix. So entities are neighbors if they share a common border. And when I say an adjacency matrix, I mean that's just basically a big panel of data which maybe you just use zeros and ones to indicate if certain types of metric values are actually adjacent to each other. I mean, there's lots of different ways that you could understand this. You could use a distance threshold, so you could think about entities that are neighbors and within a certain distance of each other. I mean, I use distance-based analysis, distance-based thresholds in my work every single day. So at the moment, I've been working on a problem in Peru. So I've been helping to plan some wireless networks in Peru, and one of the key issues there is that actually if you use wireless connections it's often a lot cheaper to connect people to the internet than use a fiber cable, for example, fiber optic cable, which can provide lots of capacity but is expensive, more expensive per square kilometre. And the problem with wireless links is that they're great and they're very cheap, but they can't you can't beam much capacity over more than 40 kilometers. So a lot of the distance-based thresholding work that I'm doing at the moment is kind of reflecting that kind of threshold point. And often I'm looking for other points, which could be cell towers or settlements within a 40-kilometer radius, because I'm interested in trying to find those points in space that we could actually route the network to. So this is something which is really commonly used, and it's a great way to kind of understand how different points in space are related. And then inverse distance weighting, so the level of neighborliness of entities, which essentially you can obtain by weighting based on how far apart they are. So I think the key point is that if I was at a point, if we were at GMU campus, for example, and I told you to walk in one direction for 2 kilometers, the number of meters that you've walked would increase as you walk away from GMU. And the point here when we say inverse distance weighting is that imagine that that increase in the number of meters is actually inverted, so it's flipped the other way. So you have a larger number when you're closer to campus, and then you have a smaller number when you're further away. And actually by inverting the distance in that way, so inverse distance, you can use it to weight how proximate things are to each other. And that's a fairly common thing to do within spatial statistics. And actually people use that to do a range of things, including trying to correct spatial autocorrelation processes. Okay, point pattern analysis. So you're going to need to read the chapter in the book affiliated with this, but we're going to be focusing predominantly on these two different types of point pattern analytical methods, so nearest neighbor analysis and quadrat analysis. So these are global methods, so basically you would carry these out for all of the data which you had. And as I said before, there's these two methods, nearest neighbor, which is kind of asking the question, well, what's the level of space that we have between these different points? And those points could represent a variety of different things. Or quadrat analysis. So this is trying to understand the overall nature of the points, potentially in terms of the frequency of points that you have within your quadrat squares. So I'll explain that to you later. In both cases, we're essentially trying to determine if the pattern is significantly different from what we would expect as a random process. So, as I mentioned in the introduction, it's very similar to the other types of kind of probability-based statistical techniques that we use to assess whether our results were, significantly different from what we would just expect to occur by chance. And these random processes, most probably can be a Poisson process. So frequencies are spatially and temporally random. And actually this comes up a lot of times within my field. So a lot of people who do these kind of spatial simulations of reality, maybe to understand how better to connect people to the internet. So a lot of engineering simulation. So imagine you have moving people and they're moving around some cell towers and you're trying to understand how to optimize the design of the network better. Well, actually they use Poisson point processes to distribute those people and those cell towers randomly. And they actually, they take a placement of those people and those cell towers and they see what happens in that one context, and then they will take another random placement of them and they're able to run the model over lots of iterations. This is called Monte Carlo analysis, where you randomly generate a distribution of points, so people and a distribution of network assets like cell towers, and then essentially you can understand what happens under all of these different random iterations. And that provides you with huge insight because you're able to capture the kind of random differences that you get as you end up with different spatial structures. So this is fairly commonly used, and we're going to be using it here in order to understand randomness across space. So let's begin with the nearest neighbor analysis. And this is in the McGrew et al. Book on page 211. And really the objective here is for us to understand if a point pattern of interest to us, which could be a variety of different things, let's assume it's community infrastructure services like fire stations or police stations, understand if their location is essentially a random process or whether it's something else. Okay, and there's actually a very nice example in the book which details this. And before we begin, we have these requirements. I already spoke about this, but essentially you can think of these as the assumptions that you might need to meet in order for the statistical test to be valid. And that includes a random sample of points and also independently selected sample points. And you can have a variety of hypotheses. So the null hypothesis here is that the nearest neighbor, the test statistic is basically broadly the same as the randomly generated nearest neighbor test statistic. Sorry, this is actually the mean. So you can think of this in terms of the observed mean nearest neighbor distance versus the random mean nearest neighbor distance. And then the alternative hypothesis, the HA value, essentially, if you were thinking of it in terms of it being a two-tailed outcome, you could just say that the mean, the observed mean nearest neighbor distance is not equal to the mean that we got randomly. Or you could state a one-tailed hypothesis. So maybe you think that this value here is larger than the value which occurs at random, or maybe you think that the value that you've observed is going to be smaller than the value that you see occurring at random. Okay, so I hope that that's fairly clear. We've been over hypotheses many times before, so that should be clear to you now. The test statistic here is a Zn. And ultimately, the way that we understand this is analogous to how we compared previous observed frequency distributions to some type of perfectly normally distributed variable. So we've been here before, essentially. This is just an explicitly spatial variant. So to find that test statistic, Zn, essentially what we need to do is get the numerator. So we need to get the observed mean of the nearest neighbors, and we need to get the random mean distance for the nearest neighbors. And we need to divide it by the standard error of the mean for the nearest neighbor distance. So this is the way that we generate the test statistic. I'm going to work out now how we obtain those particular metrics. So just to begin here, to get the observed mean, what we need to do essentially is to sum up all of the distances in the data set and divide it by the number of points that we have. It's important for me to state, though, that we're using Euclidean distance here. So this is straight line distance. We're not taking into account things like the curvature of the Earth, for example. So this is the straight line distance through space for all of the points in the data set. So let's say we've got 10 points. For point 1, we draw a distance to point 2, point 3, point 4, point 5, and we record the distance. And then we start on point 2. And point 2 has to get the distance to point 1, and then to point 3, point 4, point 4, point 5, point 6, etc., and so on. And therefore, you end up with the distances between each all of the points. So then we were able to sum up those distances and divide them by the number of points in the data set, and that gives you the mean distance, essentially. We need to calculate the mean nearest neighbor distance for a random pattern 2 in the same study area. So that's this mean value that we get here from the random distributions. And the way to do that is we basically need to take the number of data points that we have divided by the area, take the square root, multiply it by 2 to get the denominator, and then we basically divide 1 by that denominator. And that provides us with some sort of randomized mean value for what we would expect to occur. And then you'll remember from the previous slide, so that's given us the numerator to get the test statistic, but we need to get the denominator. So the way that we do that is we have to calculate the standard error for the nearest neighbor distance test. So we essentially get that standard error by calculating here. So we need to basically divide 0.26136 by this denominator. And this is pretty much analogous, so the same as, very similar to the normal standard error of the mean, which we've calculated many times before in a variety of different tests. So the mean nearest neighbour distance is an absolute measure. So it's not relative, it gives us an absolute measure in the units of distance that we use. So that's an important thing to remember, because if I gave you a set of points, you need to remember what your coordinate reference system is going to be. So all of your points are going to have some sort of number for your latitude and your longitude coordinates, your x and y coordinates, and therefore you need to know what the units are, because it's garbage in, garbage out. If you don't know what your measurement system is in the first place, getting the distance between those points is just going to be junk. So you need to make sure that that's in a sensible set of values. So maybe if it's WGS 84, so it's a global measurement system, it will be in degrees, which isn't that useful if you want to measure pure absolute distance. So you need to make sure it's in a projected coordinate, which, for example, uses meters. So you can use a transformation to get that. But that's important here because you need to know what the unit distance are. You then are able to get some standardized insight by using this other type of nearest neighbor index, essentially. So you can take the ratio of the mean nearest neighbor distance to the random nearest neighbor distance in order to get that kind of standardized insight, which gives you some sort of relative level of distance. So the R values range from 0, perfectly clustered, so R is the value for this particular index, all the way up to perfectly dispersed, which is about 2.149, with the value of 1 being just a randomly distributed set of data points. So we can think of this as a descriptive spatial statistic that we are essentially trying to find out if this value is significantly different from 1, which would just be random, for example. So in other words, similar to the Z or the T distributions, we find a Z or T so extreme, to one end of the distribution, that it gives us some level of confidence that this might be occurring as a result of some other process that isn't random. If it goes beyond some sort of confidence level that we exogenously define before we start the test, okay? So always in advance. So what do those R values look like spatially? Well, I'm going to start here by looking at the fully dispersed version. So if you get an R value of 2.1491, this is incredibly dispersed. Actually, it reminded me of the way that cell towers are distributed. Because in rural areas, for example, you're trying to optimize the placement of those cells, so you put them at very far apart distances in order to provide big coverage, and actually the pattern ends up looking quite similar to this. Not exact, because this is triangles, but normally you'd use hexagons. So actually, now I think of it, it is quite similar, because if you take 6 triangles, they form a hexagon. So this is actually very similar to how you plan a cellular network in space, essentially. So anyway, that's the fully dispersed metric. Now let's look at a much smaller R value, so below 1, so 0.5. And here you can see that we've got highly clustered points in space. Okay, so this could be a good example of this is shops, because you have malls, you have shopping districts, and generally those types of shops are going to often be clustered with others, because then you get this kind of critical mass effect. There's like a weight of gravity there which attracts people. So often you have lots of shops clustered in one place in space. And actually you could probably see this type of process. If I told you now, go off to OpenStreetMap and pull up a whole load of points, I want to look at the number of shops that are clustered across space, the level of clustering between them, I suspect you could see a pattern like this. Okay, and I think the point here is that if this is, you know, around 1, then that's almost random. So the importance of area in nearest neighbor analysis. Many of the formulas for nearest neighbor analysis need a value for area, and this is obviously going to be a problem because it means that we need to actually kind of exogenously define the study area. So if I told you to go off and look at the clustering of those retail units in space, then I would need you to draw some boundary around that. And you know, we've spoken about that in a variety of cases, whether we focused on Fairfax City or Fairfax County or the state of Virginia. These are the types of borders that we need to exogenously define. So when I say exogenously, I mean externally define, and it's down to the analyst. But the important point is that that area that you select is actually going to influence your results. So you need to be very careful of that. It goes back to, you know, the modifiable areal unit problem. Okay, so it's an issue. It's arbitrary. The definition of your study area is arbitrary. So you need to have some kind of logical reason for why you would define that space in that way. And if you're not sure about the boundary, just use a type of boundary that other people in the literature have used. So, you know, the classic example is you just use census tracts because it's a spatially granular level of insight, which also provides you with population information, and that's useful. And I think that that's fully legitimate. Okay, so there's not much more for me to say here. I pretty much summed it all up, but it will have some sort of effect on your results the way that you define that boundary. So just be aware of that. So that was nearest neighbor analysis. Now let's focus on the second technique, which is quadrat analysis. So again, we're looking to see whether a point pattern is essentially random, whether it's occurred from a random process. And you can actually follow this if you go to page 216 in Negru et al. And you can look at the different assumptions that are required in order for us to understand this test. So we need randomly sampled points, and we need points that have been independently selected from their population. We can state a hypothesis. So a null hypothesis would be that the variance mean ratio, which is what I'm going to show you how to calculate shortly, is essentially equal to 1. Whereas an alternative hypothesis might might expect that the variance mean ratio is not equal to 1 if you're focusing on a two-tailed approach, or if you're focusing on a one-tailed approach, you might specifically state the direction. So here the alternative hypothesis, one-tailed, states that the variance mean ratio is above 1, so we think that those points are going to be more clustered. So maybe this is a good way to think of the retail shopping units I mentioned before. Or over here, maybe the hypothesis where you've got a variance mean ratio below 1, so you've got more dispersion, is a good way to think about fire stations, because often they're optimized geographically to spread across the population so that you have kind of an even-ish travel time for fire crews to get to burning buildings when people need rescuing, essentially. So the test statistic is chi-squared, which we've come across before. And the way to calculate the chi-squared value is essentially to take the variance mean ratio, and then you have to multiply it by the number of degrees of freedom. So the test statistic here is a function of the variance mean ratio and the number of cells. So m is the number of cells. We subtract 1 to get the level of the number that we need here. Okay, so what does this mean in reality? Well, quadrat analysis focuses on the frequency of occurrence of points in quadrats rather than the space and spacing of points. And a quadrat is a series of regularly sized square cells. It is actually funny seeing this example in the book, because one of the very first things that I did when I started my undergraduate university degree was that we went on a field trip and we actually carried out some manual sampling using quadrat analysis. So I was in environmental science, so this is the type of thing that you might do if you're interested in species distribution and the effects that chemicals from agricultural runoff might have in one field as opposed to another which doesn't have any agricultural runoff. And a quadrat is just, imagine just a big square like this, and then you have, it's just a grid. So imagine you have a metal grid like this. And actually what we were doing was we were just randomly sampling the species that we would get in the quadrat. And to randomly sample, we would just literally chuck the quadrat in the air, and it would randomly fall somewhere. And then you'd walk over and you'd record all the points that you would take, and then you'd chuck it again, and it would randomly fall somewhere, and you'd record all the points that you got. And this is kind of a manual way that you could go off and sample plant distributions and how different environmental factors may affect their growth, for example, biodiversity. So anyway, enough of the nostalgia. I just kind of want to point out that you can do this manually. I wouldn't do it these days manually. In fact, I would look for a computational way, maybe a remote sensing way, to try and estimate those species distributions, or maybe use a drone and try and automate the speed of that so you can get a larger sample size. But if you go back to when I was at university, I mean, there was less of that around because, you know, it was 15 years ago. Okay, great. So now hopefully you understand what a quadrat is, and basically when you put the quadrat down and you draw a grid across this area, you could get, you know, points distributed across all of these cells here, which would indicate very little depth variance between the tiles, the quadrat areas. Or you could end up with something where you've got highly clustered points like this. So if you looked at population in space, you would probably end up with something like this, where if you said you wanted settlements of 10,000 people, you would probably end up with a highly clustered outcome like this if you draw a grid across it, which is actually something which I was just doing the other day, gridding population data sets. Or just down here, you could just end up with random variance. So there wouldn't be much of a pattern going on if you saw this type of frequency distribution within your quadrat cells. Okay, so that's a kind of high-level picture of what we're doing with the VMR. How do we actually calculate that, the variance mean ratio? Well, this is used to standardize the variability in cell frequencies to the mean frequency. Okay. And that means we need the VMR, so here, and we need to get the VMR by basically dividing the VAR, the variance of cell frequencies, so this numerator up here, by the mean cell frequency, which is this denominator down here. And the way that we do that is that we take the VAR here and the mean here. So let's start with the VAR. Essentially what we need to do is we need to initially take the sum of f times multiplied by x squared. So f is the frequency of cells that we've got, and x is the number of points. We also have m as the number of cells, and n as the number of points. And essentially we then run those figures through this equation here. So we've got the number of degrees of freedom as the denominator, and we've got this calculation up here as the numerator, and that gives us our VAR value. And then down here, this is much simpler. So just to get the mean, we just need to divide the number of points by the number of cells that we actually have. So this gives us the mean value. And that allows us to calculate this VMR. So a few extras. The number of degrees of freedom that chi-squares has is m-1 for this test. So I spoke about that earlier. I also emphasize that in all of these tests, because you're including space explicitly, the modifiable areal unit problem is going to be a significant issue, and you need to consider that, particularly if you're carrying out a dissertation topic. You need to make sure that you recognize this, and actually if you look at one of David Wong's papers from actually a couple of decades ago now, he was looking at the influence of drawing boundary size around statistical areas in order to then run regressions on them to understand the impact of the modifiable areal unit problem. And I think that that's a really nice thing to do, because you're able to show how the effect of this process actually influences your results, and quantifying that is incredibly strong scientifically. I mean, that would make a really nice paper. And it did. I think that's one of his most highly cited papers. Quadrat size, so essentially you need to make sure that it's big enough to fit around the visible clusters of points that you're interested in. And there's some general rules, so at least twice the average area per point. You could have regular boundaries versus regular quadrats, and you need to determine this based on the kind of process that you're studying. So as with all of these processes, it comes down to the analyst making a judgment call as to what they think is sensible based on the process that they're trying to understand. And that's challenging because it means that there's no hard and fast golden rules that I can tell you about how to do this. But at the same time, that's why you end up with people becoming, the person in a specific area, because they have so much ingrained knowledge about particularly how you apply statistics and quantitative methods to certain fields. They're able to understand how you make these calls successfully with good justification. And finally, the test only checks for frequencies inside the cell borders and not actual point locations. So similar variance mean ratio numbers may look visibly different because of border delineation. So here's just a small example for you. Yeah, so I think that's fairly straightforward, and I think that this is a nice way to graphically show that. Okay, so that was the point processes which we looked at, and hopefully you have had an opportunity now to read that in chapter 14. So chapter 14 in the McGrew book. And that sets us up nicely now to go on to chapter 15 in McGrew, which is focusing on the area pattern analysis. So within area pattern analysis, essentially we're focusing on polygons here. So actual areas, are they randomly distributed in space, or is there some of the process which is going on here which is non-random? And we use this all the time. So you will, I'm sure, in other classes have visualized data within polygon areas, whether that's looking at counties, census tracts, zip codes, states, etc., whatever geography you're interested in. And now we're going to focus on both join count analysis and Moran's eye. Okay. So join count analysis, so this is for binary categories, is actually an example within the book on page 223, which you're able to go and look at. And the point here is to determine if a random process has generated a binary area pattern. So we have some requirements. So we need each area to be a polygon, which can be assigned in a binary way to one or two categories. We need a consistent methodology for determining how proximate, so adjacent, different areas are to each other. And then essentially we need to be able to state some hypotheses for what we want to test. So a null hypothesis would be that the observed joins is equal to the expected joins. So sorry, apologies, I just noticed I need to correct this. So that's how we would get the null hypothesis. In contrast, we have the alternative hypothesis, where we would say that the observed joins are not equal to the expected joins, okay? That's for a two-tailed based approach, or we could have a directional one-tailed approach. So we could say that the observed joins are going to be higher than the expected number of joins, so we think that this process is essentially more dispersed, these areas are more dispersed. Or we could have a hypothesis where we think that the observed joins are below the expected joins, so we would expect these areas to be more clustered. Okay, and the test statistic here is ZB. Okay, and how do we calculate that test statistic? Well, essentially we need to get the numerator, which is basically we subtract the observed joins from the expected joins, and then we need to divide it by sorry, I just noticed that I need to make another change. Standard error of the joins. My apologies. Let me just get this right for you. Standard error of the joins. There we go. Okay, so that's right now, and that would provide you with the test statistic. The one thing that I haven't noted to you is this, this black-white joins approach, and that's just because it's standard. Okay, so I'll explain what that means now. Firstly, we're focusing here on areas that have a shared border. So imagine you have two squares next to each other and they share a border, they would be classed as joints. Okay, I'll show you what this means geographically shortly. We're not talking about GIS spatial joins, okay? And essentially what we need to do is categorize the aerial data. So imagine we're looking down at this geographic information and we want to categorize it into a binary distribution. And the classical practice, which I was alluding to when I say black-white joins, is because they call one group black and another one white, and they look at how many joins there are between those different categories, essentially. So this was, defined back in a day before color printers. so having black and white joins is one of the easiest ways to delineate the difference when you've only got black and white printed textbooks. So essentially you're able to count these different joins and understand therefore how many joins are similar or dissimilar. And that provides you with some understanding of how clustered the areas are. So if you've got a few dissimilar joins, then your areas are more clustered. Whereas if you've got many dissimilar joins, then your points, your areas are more dispersed, essentially. So we can then compare to how many dissimilar joins are expected just by a random process. Okay, if we just generate randomly a set of outcomes, we would have some understanding of how many joins we would potentially get. So, joint count analysis. The question is, well, how do we obtain the desired sample data to determine the expected number of black-white joins? So this methodological issue. There's a variety of ways that we could do that. We could just use free sampling, so we could determine the probability that areas are one or another using potentially theoretical models or reference to a much larger geographic scale. Or we could just use non-free sampling, so we could use a study area or data sampled to generate counts that we would expect based on the information that we gather. And generally, we'd see more non-free sampling methods because they're cheaper, easier to do. So, for joint count analysis, we need to carry out this example. So this looks incredibly scary because every time that we generate the standard error, we have this really long equation, I'm afraid. So you just have to bear with me. It's nothing more complicated than what you already achieved with the other tests. So we want to get the observed black and white joins and the expected black and white joins and the standard error of the joins. Okay. So OBW is the count of the observed and EBW is the expected. How do we get the expected number of black and white joins? Well, the way that we do that is we run through this equation here. So EBW is equal to 2 multiplied by J, the number of joins, multiplied by B, the number of black areas, multiplied by W, the number of white areas, and then divided by N times by the number of degrees of freedom. Okay, and that gives us this EBW. Hopefully that's not too scary and that you've done these calculations in the other classes with me and that this should be falling into place now. And we'll run through this in this example, and also we'll calculate this within the laboratory that we're going to do. So that gives us the numerator for the equation. Okay, once you've got the OBW and the EBW, we do need to calculate the standard error, and it does require us to go through this really long equation. So we need to take the square root of EBW plus the outcome of this equation minus EBW squared. Okay, and hopefully you'll be able to run through this. I mean, this looks really long, but by the time you work out that you just need to plug these numbers in here, it's not that hard. If you need to do it manually, you can do it in a spreadsheet. You just need to work out how to do each calculation. Potentially you could use one cell for each of these individual calculations. So you have 1, 2, 3, 4 cells, and then you just take the square root once you've been able to sum, and subtract. Okay, if there's any problems, let me know, but hopefully that should be fairly straightforward. So this is just an example of how we calculate that test statistic for this 6 polygon area here. So we have 4 coloured, so green here, I think it actually is, and 2 white areas from these 6 polygons, and this provides 7 area joins. So 1, 2, 3, 4, 5, 6, 7. Okay, so I hope that that was clear. So we're looking where we have adjacency between any cells. So that can take place here on the right hand side of this white cell, or above this white cell. Okay, so that gives us this outcome. And then we basically need to take into account these the test statistic equations. So I just restated it down here because I felt like there was a lot going on this tile, so you don't have to flick back. But basically, all of this middle section here is just calculating the standard error. Okay, and the standard error for the black-white joins comes out as 1. So it was actually a very nice round number to finish with. And just down here, what we try to do is calculate the z statistic. So we have we need the OBW minus the EBW minus the standard error. Well, we have 4 here for the observed black and white joins. We have the expected black and white joins, which is 3.73, which we calculated using this statistic just here. And then when we actually run through that with the standard error of the joins, what we get is 0.27. So it's quite a small value, which when you look at that in terms of the p-value is only 0.4. So really, there's not enough evidence at all for us to reject the null hypothesis. So we would say that we do not have enough evidence to reject the null hypothesis at the 95% confidence interval, for example, which is fairly standard, and therefore we would expect that we can say that this is most likely the outcome of a random process. We don't have enough evidence to say otherwise. Okay, so I hope that that's clear, and I appreciate that this is big and scary here, but by the time we break it down into these few little calculations, actually quite a straightforward calculation to make. So moving on to our final piece for today, I'm going to be focusing on Moran's index. This is actually the global variant here. We'll do the local one in a second. And essentially, you can read about this on page 229 within McGrew et al. But essentially, the objective is to identify non-random spatial patterns. So the key point is that we have some requirements we need to meet. So we need to have at least 30 geographic features in order for us to use this test. And fortunately, we can actually use ordinal, interval, or ratio attributes here. So we can use a variety of different data types. The hypothesis for the null hypothesis essentially is that the values we've got are just randomly distributed. And the alternative hypothesis is that the values that we've got are not randomly distributed. There's some other non-random process leading to them to cluster in space potentially, or all be dispersed in space. It could be either. And the test statistic is the I value, so Moran's I. And to get the I, we need to calculate this equation just here. And I thought rather than just leave it like this, I would transfer it into text so that you could just understand it a bit more easily. So to get Moran's I, we need to take the number of areas, which we do here. It's the sum of the number of areas. So it's the number of areas. And then we need to multiply it by the sum of the cross-pair products for all contiguous pairs for I and j. Okay. And then on the denominator, we need to take the number of joins that we've got within the data that we're interested in. And we need to then also take the variance of the area attribute values. Okay. So that's how we get I. So the test takes into account the actual attribute values to determine if these values are random, clustered, or dispersed. So if the I is below 0, then we would say that these points are dispersed across space. If I is above 0, we would say the antithesis, so the opposite. We would say that these points are actually clustered in space, very close together. Or if we find an eye around 0 or in this space, then we would say that they're pretty much randomly distributed and that there's not a strong spatial pattern taking place influencing their location. And we can actually use this on both points and areas, and we can determine neighbours, so for contiguous areas. And we can also take into account inverse distance weighting, for example, as one way to include space here. Okay. So I think we've been over this, and it's fairly clear already. So let's progress. So what we need to do once we get I is to basically get the z-score. The way that we do that is by using this equation up here. So Moran's I will range from -1 to 1, as we mentioned before, and we can use that in the numerator to get the z. But we also need to get this EI score here, and EI is the expected value. And to get that, we basically need the number of samples in the data set -1, so the number of degrees of freedom, and we need to divide -1 by that value, and that gives us the expected value. Okay, and then we also need to calculate this this denominator here. It's actually quite complex, so we'll just do this in ArcGIS later, rather than trying to run through and manually do it. So the local variant of Moran's I enables us to actually calculate an autocorrelation score for an individual object within a data set. So maybe that's a neighborhood or a city within a much larger geographical area, such as a state, for example. And this can provide us with hotspots of spatial autocorrelation. The formulas are similar to the global measures, which we mentioned before, but with some more complicated procedures to apply to each local object. So let's just focus on the output. So this is just an example which is used in the text, which focuses on racial segregation within Detroit. And here this choropleth map essentially is indicating the racial homogeneity of different areas, essentially. So this is actually the percentage of white people, so under 20% in these lighter areas and over 80% in these darker areas. And actually you can then run a Moran's I for these data, and actually what you get is quite a very strong results. So Moran's I here is actually 0.887, so you remember that Moran's I only runs between -1 and +1, so this is actually indicating a very, very high positive level of spatial autocorrelation, with a z-score of 48.26, leading to a very small p-value. So essentially, when we actually interpret the data from running this Moran's I test, the z-score is indicative that there's less than a 1% likelihood that the cluster pattern could have occurred just at random. So this is a highly clustered process, essentially, the differences in racial segregation within Detroit. Okay. And you're also able to run some local Moran's I's in order to look for specific clusters. So I've added a little bit of extra context to interpret the map on the left here. So when you get a Moran scatter plot, it actually divides the classification of spatial areas into 4 categories, which you'll see down here in the bottom right of the slide. And essentially those categories are referred to as high, in terms of above the average positive correlation, or you can have low, high, or high low relative to the mean, which is the center area of the graph. The mean is in the middle here, and you have outliers on each of these 2 areas here, or you have low in the bottom left hand corner. So the point is that we can actually categorize these clusters based on the autocorrelation across space and the degree of clustering. And so it's actually quite nice. You can run the stat and get the general statistics, but then you can also project back to the local area and provide some sort of geographical insight into their degree of clustering and how they're centered around the mean, for example, above or below the mean. Okay, so I appreciate that that is a lot of content. We've had to cover quite a few different chapters. We are getting to the main parts of this entire module. So we've gone from really quite basic statistics through to some aspatial inferential statistics, and now we are getting to some of the main inferential statistical techniques, as I've covered today, which I think are the most exciting. And particularly if you want to stay in spatial science, then these are some of the potentially the most used statistical techniques that you might apply in your career. Okay, so watch out for the lab. I'm going to post that up next. It'd be good for you to run over that. There will obviously be some assignment work associated with the work that we've been doing this week, so make sure you get that on time. And if you haven't had a go yet at the midterm test, then best of luck for that. I look forward to seeing your results. So thank you very much. Have a great day, and I'll see you all soon. Goodbye.